Hi everyone, welcome to my YouTube channel. In this video, we are going to discuss on tutorial 20 topic X-ray. And before you watch this video, make sure you have done the question given in the link below this video. Question 1. The energy levels for the K, L and M shells of silver are as listed. K shell, the energy is negative 25.51 electron volt. L shell, negative 3.56 electron volt. M shell, negative 0.53 electron volt. And determine the wavelengths of the K alpha and K beta peaks when electrons strike the silver target in an X-ray tube. So K shell is the shell nearest to the nucleus atom, followed by L shell and then M shell. So we are going to find the wavelength of the K alpha. So K alpha is the photon emitted when the emptied electron in the K shell is filled in by the L shell. Okay, L to K. So from L to K, the formula we are going to use, the change in energy equals to HF. So the change in energy is EI minus EF. So that's mean EL minus EK. So equals to H C over lambda. So substitute F equals to C over lambda into the equation. Next, we substitute the energy given. L shell is negative 3.56 minus EK is negative 25.51. And this is and they are in electron volt unit, so we convert to the joule unit, multiplied by 1.6 times 10 to the power of negative 19. Then we also substitute the Planck constant and the speed of light. So cross multiply, we get wavelength equals to 5.66 times 10 to the power of negative 8 meter. So convert to nanometer, we get 56.6 nanometer. Okay, next we are going to find K beta. So K beta is the photon emitted when the electron from the M shell fill in the empty space by the empty space in the K shell. The electron that is kicked out in the K shell, so it's filled in by the electron from the M shell. Okay, M to K. So the change in energy is equals to HF. So the change in energy is EM minus EK equals to HC over lambda. So we substitute the energy at M shell, 0.53 electron volt. Don't forget to bring along the negative signs. Okay, minus the negative 25.51. Then we convert to joule multiplied by 1.6 times 10 to the power of negative 19. So equals to Planck constant times the speed of light divided by wavelength lambda. So cross multiply, we get wavelength 4.97 times 10 to the power of negative 8 meter. So convert to nanometer, we get 49.7 nanometer. Okay, now we go to question 2. Okay, question 2, the graph shows the intensity against wavelength for X-rays produced from an X-ray tube. Okay, intensity against wavelength graph. Find the potential difference between the anode and cathode which would produce the above graph. Okay, for a question from the graph, okay, what happened is there is a series of wavelength produced, okay, by the X-ray tube here, X-ray tube. So the X-ray produced is given in the graph below. The intensity of the X-ray produced given in the graph here is intensity against the wavelength. Okay, so this is the schematic diagram for the X-ray tube, 2-dimension diagram. Okay, this is the cathode where the electron is emitted by the filament here, and then the target is the anode. Target is the anode. Okay, so we are going to find the potential difference. So this voltage. Okay, the potential difference between the anode and cathode here. Okay, the formula we are going to use is from the principle of conservation of energy. So energy of the electron here is given by E times V. V is the potential difference here that we are going to find, and E is the charge of the electron. So equals to the X-ray photon emitted equals to HF. So F is C over lambda. So the lambda we can substitute, we can get from the graph here. So this is the lambda, okay, lambda minimum given. So 5.2 times 10 to the power of negative 10 meter. So Planck constant and speed of light substitute into the equation, and the charge of electron is 1.6 times 10 to the power of negative 19, and then the V we get is 2.39 times 10 to the power of 3 volt. So that's the potential difference between the anode and cathode, which would produce the from the above graph here. Okay, question B. Sketch the X-ray spectrum obtained if the potential difference between the anode and cathode is greater than the value in A. So label the spectrum as Q. So this is the initial spectrum given. So we are going to label the we are going to sketch the new spectrum, which is spectrum Q. Okay, so the voltage given is higher than the 2.39 times 10 to the power of 3 volts. So for the V higher, from the equation here, EV equals to HC over lambda, the wavelength. H is a constant, C is constant, and electron charge also constant. So now we can see from this relationship between V and the wavelength. So when we increase the V, so the wavelength decreases. So that's mean when we plot, when we sketch the graph, so the wavelength here 5.2 times 10 to the power negative 10 is shifted nearer to the origin here 0, and the characteristic line, these two characteristic line must be drawn on top of same level, same line as the previous initial spectrum. Why? Because the target used in this question is the same target. So that's how to sketch the new X-ray spectrum, and the question asks to label the spectrum as Q. So you must label it. So that's the answer. Okay, question 3. Explain the following: the continuous X-ray spectrum, the characteristic X-ray spectrum, and the minimum wavelength of X-rays produced from an X-ray tube. Okay, the continuous X-ray spectrum. What is the continuous X-ray spectrum? So most electrons do not undergo head-on collisions with the atoms of the target material. So these electrons are stopped after many deflections. So these encounters produce protons of various frequencies, thus resulting in a wide range of wavelengths. So hence, a continuous X-ray spectrum is produced. Okay, next, the characteristic X-ray spectrum. So the sharp points from the previous question, we can see the two sharp point from the spectrum. So that is called characteristic X-ray spectrum. So an electron with high energy collides with and removes an electron from the innermost K shell of the target atom. So K shell is the nearest to the nucleus atom, the shell that nearest to the nucleus atom, the innermost K shell. So thus a vacancy is created, so which is filled when an electron from the L shell falls into the K shell, emitting a photon. So we call this as K alpha just now. This produces the K alpha line in the characteristic spectrum. Okay, when the electron from the innermost K shell is removed, the resulting vacancy may also be filled by an electron from the higher M shell. So this results in the emission of photon producing the K beta line of the characteristic spectrums. So we have K alpha and K beta, two sharp points. If we draw or if we sketch the graph intensity against the wavelength as given, we can see or observe the sketch from the previous question. So the K alpha line is more intense because the vacancy in the K shell is more likely to be filled by an electron from the nearest L shell. So hence this process occurs more frequently. So that's why the two characteristic X-ray spectrum has different level. Okay, so K alpha is more intense. So next is C. So what is the minimum wavelength of X-ray produced from an X-ray tube? So from the graph we can see the minimum wavelength which is at the x-intercept. We can see from the x-intercept of the graph of intensity against the wavelength. Okay, so the minimum wavelength of X-ray occurs when all energy of the accelerated electron is converted into an X-ray photon in a single collision. So that is the minimum wavelength. Okay, now we go to question 4. State the factor which determine the values of the wavelengths of K alpha and K beta, or L alpha and L beta peaks. Okay, so from the diagram here, okay, so this is K alpha and this is K beta, okay, photon emitted when the electron from the L shell fill in the empty space in the K shell, and K beta is the photon emitted when the electron from the M shell fill in the empty space here of the electron. Okay, so the factor which determine the values of this K alpha and K beta, or L alpha and L beta peaks, is the type of metal used as a target. So different metal used will give the different K alpha and K beta. So if we plot the characteristic line, so it will if we compare the two characteristic line from the two metal, they will not on the same or not on at the top of each other if we draw together in the same graph. Okay, now we go to question 5. An X-ray tube produces a potential difference of 35 kilovolt between the anode and cathode. Calculate the minimum wavelength of X-ray produced. Okay, so this is the target. Okay, this is the target is the anode, and the electron produced here is accelerated toward the anode. So here this is a cathode. Okay, this is connected to the negative terminal of the supplier here. Okay, the formula we are going to use is EV equals to HF, and F is C over lambda. So the voltage given is 35 kilovolt, so convert to volt, and the electron charge is 1.6 times 10 to the power of negative 19. So substitute the Planck constant and the speed of light c into the equation, and we get the wavelength equals to 3.55 times 10 to the power of negative 11 meter. So this is the minimum wavelength of the X-ray produced. Okay, question 6. Electrons in an X-ray tube are accelerated through a potential difference of 40 kilovolt towards a target. So as a result, 600 joule of thermal energy is produced per second. However, only 1% of the energy supplied by the electrons is converted into X-rays. Find the average rate at which the electrons strike the target. Okay, from the question here, so electrical power supplied. Okay, we use the principle of conservation of energy. So from the electrical supplied energy, yes, we can also use power, because energy is Power is energy per second. Energy per second. Produce energy P equals to E over time. So joule per second unit. So we can use also electrical power supplied equals to thermal energy produced per second plus the X-ray energy per second. So the energy produced is only 1%. The thermal energy produced, that's mean is 99%. So the electrical power supplied is 100%. So this is from the initial, the power supplied. Okay, so now given 600 joule here is produced, thermal energy produced. So that's mean 99% is the 600 joule per second. So for the electrical power supply, 100%, we can use the ratio method here. And cross multiply, we get the power supply is 606.1 watt, right? Or joule per second. Okay, 606.1 watt. Okay, so the power is equals to IV, and we are going to find average rate. So average rate, that's mean the photon per second, number of photon per second. So we can get from the I here. So I is the Q over T. So from Q equals to IT, so we get I equals to Q over T. So Q is the charge of the electron divided by the time. Okay, Q is NE because there are n number of electrons. So the average rate will be N over T. So this is what we are going to find. So the average rate is N over T. So we cross multiply VE. So 606.1 divided by VE. So we substitute the voltage used in this X-ray tube. 40 kilovolt convert to volt, and the electron charge. So we get the average rate is 9.47 times 10 to the power of 16 per second. Okay, question 7. The beam of current of 10 milliampere is accelerated through a potential difference of 35 kilovolt in an X-ray tube. So find the number of electrons colliding with the anode per second. So we do question A first. You are given current and the voltage. Okay, so the number of electrons colliding with the anode per second. So we can use the same formula just now. Q equals to IT. So Q is NE. So the number of electron per second will be N over T. So cross multiply E, we get I over E, and substitute the current here, convert to ampere, and the electron charge. So we get the number of electrons colliding with the anode per second is 6.2 per second. Okay, for question B, the power. So the electrical power supplied to the X-ray tube. So the power is equals to IV. So I is current 10 milliampere, convert to ampere, and the voltage is 35 kilovolts, so convert to volt, and we get the power 350 watt. Okay, for question C, the energy in the form of X-ray produced each second if the efficiency of the X-ray tube is 0.8%. So the efficiency is 0.8% only. So the power supply is 350 watt. So not all 350 watt or joule per second energy here used in the to produce the X-ray. So the efficiency given is only 0.8%. So we use formula efficiency output power over input power times 100%. So we substitute 0.8%. So the electrical power supply is 350. This is the input, the power supply. Okay, so we cross multiply, we get X-ray energy produced per second, or the output power equals to 2.8 watt. So that's the answer for C. Lastly is the heat dissipated. So the heat dissipated per second. So the heat energy dissipated per second is thermal energy. Okay, thermal energy. So we can minus the 2.8 watt. So 350 watt minus 2.8 watt. Okay, this one is from the principle of conservation of energy. So 350 minus 2.8, so we get 347.2 joule. So that's the answer for question 7. Okay, question 8. Show that diffraction is not observed if the X-ray wavelength is larger than twice the distance d between two adjacent planes of atoms in a crystal. Okay, we use Bragg's equation, 2d sine theta equals to m lambda. So sine theta equals to m lambda over 2d. So we consider m equals to 1. Okay, and diffraction is not observed when sine theta larger than 1. Okay, that's mean sine 90 degrees with it, which is not possible. Sine 90 degrees larger than this 90 degrees. Okay, so we substitute into here sine theta, which is m lambda over 2d. Okay, and we substitute 1. Okay, so cross multiply, we get lambda larger than 2d. So it is shown here, okay, that X-ray wavelength is larger than twice the distance will not be observed. Okay, if we refer to the diagram here, two-dimension diagram, so this is the atoms crystal. Okay, so there are many family plane crystals, so let's choose this plane. Then this is the incident electron is incident to the plane, and the theta, we get Bragg's equation here. The theta is this one, the theta here, and the d is the separation between the two plane, d. Okay, so when this theta is sine 90 degrees, so diffraction is not possible to occur. Okay, now we go to question 9. A beam of X-rays of wavelength 1.28 times 10 to the power of negative 10 meter is incident on a crystal. Given that the spacing between the lattice planes is 2.19 times 10 to the power of negative 10 meter, determine the range of orders of diffraction which is not possible. Okay lah, wavelength is given, spacing, separation between the two planes given. So we are going to find the range of orders of the diffraction, which is not possible. So from the Bragg's equation, 2d sine theta equals to m lambda and sine theta equals to m lambda over 2d. So diffraction is not possible if sine theta larger than 1. So we substitute m lambda over 2d into the equation. So we cross, we are going to find the range of m. So we are going to find this m. So what wavelength is 1.28 times 10 to the power of negative 10. Okay, spacing, we substitute into the equation and we get m larger than 3.422. So the diffraction of order equal to 4 and above are not possible. Okay, next we go to question 10. Monochromatic X-rays impinge on a crystal in which the spacing of the atomic planes is 0.5010 nanometer. So the first order diffraction maximum occurs when the incident and reflected X-rays makes an angle of 30.0 degrees with the crystal planes. Find the wavelength of the X-rays. So you are given D 0.5010 nanometer. So M is the first order, theta, so wavelength. So we use Bragg equation, 2d sine theta equals to m lambda. So lambda is 2d sine theta over m. So we substitute the d given, convert to meter. Okay, sine angle is 30 degrees and m is 1. So we get the wavelength 5.01 times 10 to the power of negative 10 meter. Okay, question 11. X-rays of wavelength 0.126 nanometer are incident on a crystal whose atoms are in planes which are separated 0.212 nanometer apart. At what angle must the X-rays be directed if the first diffraction maximum is observed? So lambda is given, D is given. So now we are going to find angle, diffraction angle. So M is 1, first diffraction. So we use Bragg's equation, 2D sin theta equals to M lambda. So sin theta equals to M lambda over 2D. So we substitute all the values given in the questions. Okay, so we get angle 17.3 degrees. Okay, so that's the end of tutorial 20, and see you in the next tutorial.